Welcome. In this podcast, we're going to be graphing f of x equals x to the fourth minus 2x squared plus 1. So first, let's use the leading term to determine the end behavior. Right, so our leading term is always the term that has the greatest exponent. If your equation's in standard form, it's the first term. If it's not in standard form, then, well, you should put it in standard form first. But it's always going to be the term that has the largest exponent. So our leading term is x to the fourth. Right? The leading coefficient is the coefficient in front of x to the fourth. Oops. Trying to write the word coefficient here. Coefficient. Right, so if we look in front of that term, the leading coefficient is 1, and that is a positive number. Right, so our degree is even. And the leading coefficient is positive, and so that means that our graph is going to have this shape. It's going to look kind of like a W. Right, that's going to be our shape. All right, so first we're going to find the x-intercepts. No greatest common factor here. Right? And actually, before I do anything, I'm going to set it equal to 0. X to the fourth minus 2x squared plus 1 equals 0. I'm just going to put the 0 on that side. No common factors there. Right? Only one of the terms doesn't have an x. Right? Coefficients are 1, 2, and 1. Nothing we can factor out. All right, so we can use the rational root test to determine possible factors and longer synthetic division to factor. And then we'll set our factors equal to 0 and solve for x. Make sure that you have all the steps when you're solving. If your work does not support your answers, then I can't support them either. All right, so your work has to support your answers and be mathematically correct. Right? And no breakages in your steps. All right, so if we're going to use the rational root test, and any time that you're using synthetic division, I should see the rational root test. Oops, not the rational rot test, but the rational root test, so that you know what are your possible solutions. Right? So rational root test, we take the factors of the constant term, and divide that by factors of the leading coefficient. I'm just going to abbreviate LC. Right? And so those are going to be our possible solutions. And our numbers are really small to work with. Right? So the constant term, our only factors are positive and negative 1, right? Because our constant term is 1. Leading coefficient, we said before, is 1. So our only possible solutions I should say our only possible rational solutions. So when I say solutions, what I do mean is our only possible rational solutions. We're not going to be able to find irrational solutions using synthetic division. Not at least until we get it to something that's factorable. So these are our possible rational solutions. So the only choices are positive 1 and negative 1. That's it. All right? So not a whole lot of choices here on the synthetic division. Just pick one. All right? Pick either one. I'll take the 1. All right? So I am going to use synthetic here. Remember that for long or synthetic, this is, I'm going to write it over here. Don't forget your placeholders. Right? We have missing terms. Otherwise, you're going to get wrong answers. All right? So we have x to the fourth plus 0x cubed. And then we have an x squared. We don't have an x. And we have a 1. All right, so that's what we need to use with synthetic division. We have to represent that missing cube and the missing x. All right, so I'm going to try 1. All right, and if I try 1, I've got well, let me write the rest of the problem here. 1, 0, negative 2, 0, 1. So I bring down the 1. 1 times 1 is 1. Add, I get 1. 1 times 1 is 1. Add, I get negative 1. Negative 1 times 1 is negative 1. Add, I get negative 1. Negative 1 times 1 is negative 1. And add, I get 0. So that one is a solution. Right? This is the remainder. This is the constant. This is x squared, and x cubed. And if I had only just a teensy-weensy bit more space, I'd have enough space to do the last little part. So let's write our equation. I'm going to just add another page. So we've got x cubed. So I'm going to write the equation here, and then we're going to go to the next page. We have x cubed, and then we have x squared minus x minus 1. And we'll set that equal to 0 to solve. Now, if you notice, there's a little pattern here. I've got the first two terms have or x raised to a power, right? And the greatest common factor there is x squared. Second two terms, negative x and negative 1, they're both divisible by negative 1. I wonder if we can use factor by grouping now and switch from using synthetic division now that we've got it like that, right? Maybe I'll instead of changing pages, maybe I'll squeeze it over here. Right? So maybe if I wrote smaller, I'd have no space. So we have x cubed plus x squared plus negative x minus 1. So the first two are a group, and the second two are a group. I think I can squeeze it in here. So we'll factor out the x squared, the greatest common factor, and then if we divide both those terms by x squared, we have x plus 1. Greatest common factor for negative x and negative 1 is negative 1. We'll factor that out. We've got x plus 1. So now we have our repeating x plus 1. We can factor that out. We're left with x squared minus 1. And if you remember, we learned in a lesson when we were looking at factor by grouping, we learned how to factor a difference of squares. And remember, it is a little shortcut there. It's always going to be the square root plus the square root and the square root minus the square root. I'm giving ourselves just a teensy bit more space. A teensy bit more space, I can fit the rest of this problem here. There we go. Moved everything up. All right, so we can factor that x squared minus 1 very easily. And I do want to see the x squared plus 1 minus 1 factored, right? Don't just give me solutions, factor it. It's one step. And I'm okay if you do in your head. If you remember, it's going to be square root plus square root. Square root of x squared is x, square root of 1 is 1, and it's going to be square root again, x, minus square root. It's going to be x minus 1. So anytime you have a difference of squares, perfect square minus perfect square, it's going to be the square root plus the square root minus the square root. So x squared minus 1 factors to x plus 1 and x minus 1. Let's find all of our solutions here. All right, so let's find, I'm going to put over here our solutions. It's a good idea to write everybody down so you don't forget them. Right? Because you might forget that one right there. Right? So we have x equals 1. And then we factored, and we would set our factors equal to 0. I think we can just put the solutions now. So if x plus 1 is 0, we'd subtract 1, x equals negative 1. And again, x would equal negative 1. And if x minus 1 equals 0, add 1 to both sides, x is 1. So notice that all of our possible solutions were actual solutions. All of our possible rational solutions were actual solutions. Both positive and negative 1 were solutions here. And not only are they solutions, but they're all solutions that appear twice. So our two solutions, x equals 1 and x equals negative 1, are both multiplicity 2. Right? Both of them. Right? So that's going to be important for when we graph, right? Because we know that our graph is going to do something different if we have multiplicity 2 than if we have multiplicity 1. And we have, now that we've found our x-intercepts, we can just get the rest of our information and graph. But before we do that, I wanted to go over another way that you could have found your x-intercepts. Both are perfectly acceptable, right? So long as you show the proper steps that keep the relationships. It's not about getting answers. It's about properly being able to notate your work, properly being able to see the sequence, right? That is actually very important, because what you communicate about your work is just as important as what your answer is, if not more important. All right, so we could use substitution. Anytime you have a 3 terms, you've got, and 2 of them have an x and 1 is a constant, and the 2 x terms have exponents that where one is double the other, you can use substitution. So if you have x to the 4th plus or minus x squared plus or minus a constant, or x to the 6th plus or minus x cubed plus or minus a constant, right, you can use substitution. If it's factorable, you'll be able to solve it. And if it's not factorable, then you'll know to go back to the other technique. Right? So there's always going to be kind of a pattern to these when they are, but it's worth trying and seeing if they're factorable, because it's not a whole lot of work. All right, so here's our steps. We're going to replace x squared equal to w. Right? So where we see an x squared, we're going to replace it with a w. That means we're going to replace the x to the 4th with w squared, because x to the 4th is just x squared squared. Right? So if x squared is w, x squared squared is going to be w squared. And so now we've reduced that so that it's just a quadratic. But we don't want to use x's because x has a certain value. Right? We're going to use w's because that's just x squared. So we have w squared minus 2w plus 1. Right? And this one actually is a perfect square. So the factoring is really easy on it. But we'll do all the steps for factor by grouping. If you recognize it, it'd be okay to just go right to the factors, but do include the factors. All right, so multiplies to give us 1, right? 1 times 1, right? A is 1 and C is 1. So 1 times 1 is 1. We need 2 numbers that multiply to give us 1, but add to give us our b term of negative 2. And of course, that's going to be negative 1 and negative 1. All right, so we keep the w squared. We replace the negative 2w with a negative w and another negative w, and we keep the 1. And the first 2 are a group, and the second 2 are a group. And then we'll pull out our greatest common factor, which for the first pair is a w. W squared divided by w is w. And then w divided by w, of course, is going to be 1. And of course, it's going to be negative 1 because there's a minus, there's a subtraction. And then the greatest common factor for negative w and 1, of course, is going to be negative 1 because we want it to match our w minus 1. And we can now factor out that repeating w minus 1. And then the other factor is the leftover w minus 1. And if you said your answer is 1 and 1, you're going to have a very wrong graph. Because remember, we're solving for x, not w. So we need to replace that back. All right, so we're going to take those w's and make them x squared. So now we're going back the other way. All right, so instead of w, now it's x squared again. So I've got x squared minus 1 times x squared minus 1. Right? And remember, difference of squares, this is going to factor to square root plus square root minus square root, and square root plus square root, and square root minus square root. So now we can see that we've got x equals negative 1, x equals 1, x equals negative 1, x equals 1, and we can see they're all multiplicity 2. Right? So 2 different ways to get to be able to find your x-intercepts. Both are fine. Just make sure you've got your work properly notated. All right? So now we got the x-intercepts. We need the y-intercept, and we need our turning points. All right, so I've already plugged this one in for us. And this time I just plugged the number in. But let's go through our possible turning points. Right? And I didn't erase this one. I am hoping I erased the graph on the next page and didn't forget to just erase that. Oh, I did erase that one. Good. All right, so let's take a look here at any day now. All right, so we're going to use the x-intercepts to divide the graph in intervals and test a point in each interval to graph. Right? So when we take a look at our two x-intercepts, we've got -1 and we've got 1. So what's the only integer between -1 and 1? Well, that's 0. Well, if we plug in 0, what's that? Well, of course, it's our y-intercept. So the y-intercept gives us a clue as to the behavior of the graph between the x-intercepts 1 and -1. The graph increases from -1 to 0 and decreases from 0 to 1. That's our turning point, and it's going to, since it's positive, it's a positive number, it is our relative maximum, even though it doesn't seem like very max. 1 is our relative maximum. Right? So our function is going to come from above. It's going to touch the x-axis at -1. It's going to go up to the y-intercept at 1 there, and then it's going to go back down to the x-axis, and we have our other x-intercept at 1, and then it turns, because they're both multiplicity 2, and goes back again. We've got 3 points. So it's kind of hard to figure out maybe why to make your graph when you're coming down. 3 points isn't very much. If you're left with 3 points, why not go ahead and plug in another point? So I chose 2 and -2. Right? And I'm not going to go over step by step the multiplying and adding there, but notice we get 9 and 9 from both. This is one symmetric graph. Right? So we've got our two x-intercepts are -1 and 1. Smack in the middle is our turning point. And then on either side, we've got 2, 9 and -2, 9. It's a very, very symmetric graph. And actually, this is a special kind of, it's not even just even degree, it's actually what's called an even function. So even degree and even function are different. You don't have to be polynomial to be an even function, but what you do have to be is symmetric about the y-axis. So that will help us. We know our graph has to look exactly the same on the right-hand side of the y-axis as it does on the left-hand side. Right? So if I didn't put that in your notes, even function is symmetric about the y-axis, go ahead and write that in. And there's not a whole lot else to write in here because I think everything else is in your notes. And let's graph. And we can graph this one lickety-split because it's a pretty easy one. All right, so we've got our two x-intercepts, right? -1 and 1. And there we go. We have our y-intercept, which is 0, 1. And so now you can see why I said, oh, you should probably put in 2 more points. Because I don't know how many times somebody will tell me, oh, it looks like this. Whee! Of course we know it can't look like that. That's not a W. And it's not even going the right way. Our leading coefficient is positive. All right, so we have our other 2 points. So we have 3 relative extrema here. We have our x-intercepts, our relative minimums. Our y-intercept is our relative maximum. So everything gets to do double duty. All right, so let's graph -2, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this graph is going to, and then 2, 9, is going to look incredibly like a W. All right, and so then just remember your end behavior, and then we'll graph. So f of x goes to, right, so remember this is even degree. Both ends go up in the air, right? So it's going to go to infinity as x goes to -infinity. And it's going to go to infinity as x goes to positive infinity. So I need to start my graph high, as we can see by our points here. And then we're going to head down to the x-intercept and turn, because it's multiplicity 2. And that's our turning point. So I got to turn again. Multiplicity 2. Got to turn one more time. And you're going to go right through your other point that we found to help us graph our graph a little bit better. And look at how symmetric that is. Can you be more W than that? The last thing we're going to do is, we've already got domain there. All of our polynomial functions have a domain of all real numbers. We just need the range. Look at your graph. What's the low point? Well, I hope you said the x-axis. Right? It does touch the x-axis. So we've got 0 with a bracket as our low point, and then both ends go up to infinity. Right? So there's our range. And it makes perfect sense, by the way, why all the numbers are positive. You've got x to the 4th and x squared. Nothing but positive numbers. And x to the 4th is going to grow faster than x squared. Right? So even though you're subtracting, you're always going to have nothing but positives, and that's what we got. All right, so that's the end of this one. The next podcast, we're going to graph one more. All right, bye for now.